The purpose of this lecture is to introduce concepts involving electric charge and Coulomb's law. These are the basic themes that we're going to be working with, and in this lecture, we're going to go all except for the bottom on this list. And then I'll have another lecture that covers the second half of the chapter. So we'll start off with this ridiculous picture, which is kind of traditional, but like I said, it's ridiculous because there's no sense of scale here. There's just an idea about relative concepts. So we know that the nucleus is a relatively dense, not relatively, extremely dense particles. Some are charged and some are not charged. So protons are charged, neutrons are not. Electrons are orbiting this in sort of a planetary model, but that doesn't really work either. We'll talk about quantum mechanics at the end of the semester. But the scale is, of course, terribly wrong because if I was a nucleus, my electrons would be hundreds of miles away. So that's important to keep in mind. But the big takeaway from this is that positive charges are not going to move. The only way we talk about something being charged is by motion of electrons. So the classic, if we rub a cloth on a piece of plastic, then we can make it charged. But what charged means is that it's either going to be electron deficient. That means not having enough electrons to equal the number of positive charges in atoms and excess electrons. So how does something get electron deficient or have excess electrons? And the answer is that it depends on the chemical makeup of whatever the materials are. So like in the case of plastic, plastic are made from hydrocarbons, and the hydrogen atoms tend to sit on the outside of the molecule, experiencing covalent bonds. So their electrons are very busy, and they're busy with the internal parts of the molecule. So these hydrogen atoms have their electrons spending much of their time on the interior part of the molecule, which leaves it sort of, kind of wanting an electron. So it's very easy for plastics to pick up extra electrons. Water, our favorite molecule, in itself is polarized because here we are with the hydrogen atoms, and this is kind of demonstrating the point that they only have a single electron. That electron is involved with a covalent bond with the oxygen. So that means that the electron is going to spend much of its time inside, leaving this net positive. And likewise, two electrons from the oxygen molecule are being involved in a bond with hydrogen. And so that leaves its outside as kind of negative, a little bit. Conductors and insulators, most people should be pretty familiar with these concepts. And again, it has to do with valence electrons and how easy it is for them to move. So with metals, just like they're very good conductors of heat, they're also very good conductors of electricity. And that means that they have valence electrons that are not bound very strongly, so it's easy for them to flow. Here's a couple of different ways that you can make things charged. So if we have a metal object that's electron deficient and we put it in contact with something that's neutral, then it's quite possible that since this is so electron deficient, it might suck some electrons across and then leave this rod electron deficient. So in general, in the end, they will have shared that electron deficiency, and this one won't be as charged as it was before because it will have shared that notion of being charged with the other object. So this is called charging by conduction, and conduction requires contact. This is a slightly sneaky way of charging something, and it's called charging by induction. It also involves ground too, which is a really important concept to get off the ground. So it's an infinite supply of whatever charge you need to neutralize an imbalance. If we have a conductor and we bring a negatively charged conductor nearby, so this has excess electrons, and we bring it nearby, that's going to drive electrons away from this object, leaving it electron deficient. And so if we remove ground, again, ground is an infinite supply, whatever we need to neutralize a situation. So When electrons here get moved away, then it makes this entire situation rather neutral. Now, if we take ground away and then take this away, then we will have left this electron deficient. And notice that the sequence of that is really important. We take the ground away first, and this leaves this overall neutral. And then the negative charge goes away, and we're left with a positive charge. So by charging by induction, we can actually engender the opposite charge. And we're all familiar with a balloon sticking to the wall, and how does that work if the wall wasn't charged in the first place? So a latex balloon, very easy to get a charge because it's got, like I said, it's got all those hydrogen atoms. It's made, the latex is made of polymers that have a lot of hydrogens on the outside of the molecules. So it's easy for them to pick up extra electrons. And when they're brought in the presence of a non-conductor, it can induce polarization. So therefore, we have three different ways that you can charge: conduction, induction, and polarization. Coulomb's law is one of the very few forces that act at a distance in our universe. Gravity is another one, and then there are only two more. There is the strong nuclear force and the weak nuclear force. So that's it. There are only four forces that act at a distance. And we're still trying to understand the nature of this. Modern physics is operating under the assumption that in order for these forces at a distance to take place, that there must be some kind of particle exchange. And those particles may or may not travel at the speed of light. So Coulomb's law says that it takes two objects in order for an electric force to exist. And we know that's a natural outcome from Newton's third law, which says that any force is an interaction between two things. You can't really have a force just sort of sitting there. You have to have something able to detect that force. And it's actually closely aligned with the concept of a field, which we'll talk about in the next video. But two charges, and they're represented by Q1 and Q2. K is a Coulomb constant, and it just has numbers that get the units to all work out right. And then divided by r squared, which would be the distance between their centers. And it's r squared too, which is a really interesting concept, because the other major force that acts at a distance is gravity, which was studied in Physics 1. And that too is an inverse square law. So that interesting connection between inverse square laws is something that, and beyond that, same thing, two masses. And so the similarity between these two forces was really a big driver in Einstein's work in the latter part of his life, as he worked on a grand unification theory and never really finished it. Now, I find this notation really confusing. So if you're reading this in the textbook, don't pay too much attention to this, because I'll show you in a tutorial how to work around this. But the Coulomb constant is very, very large. So in our tutorials, I'll make sure that we talk about how to use these large numbers on your calculator. And because this constant is so large, but the charges themselves that we're dealing with are so small, that we'll be using the micrometric prefix quite a bit for 10 to the minus 6. So one of the typical units of charge that we'll talk about is the elemental charge, which is the charge carried by an electron or the charge carried by a proton. And the magnitude is shown. And it's in units called coulombs. Coulomb was a 19th century French physicist. But it is a force, and that means we're going to have to pay attention to vectors, a little review of vectors. So when we're adding two forces together, if they're not collinear, then we're going to have to resolve them into components. And so when we add them, we have to just add x components together and just add y components together. So if the original force is not given to us in components, we're going to have to resolve it into components. And the way to do that is to use the angle and the magnitude of the force. So we'll use the cosine function for x components and the sine function for the y components. But again, we'll have a tutorial that shows you how to do that. And then the next stop is electric field.